welcome to Real Physics. Today I will show you my first chat with artificial intelligence about fundamental physics. Why I am doing that? Okay, there are critics saying that these large language models are not really intelligence, they don't have conscience, and they just represent the knowledge of humankind so far, and they're not creative and whatever. I don't really want to enter in that debate. As a matter of fact, these developments have surprised us, have surprised also me, and I think sooner or later we will arrive at a artificial intelligence which is at least similar or even greater than human intelligence. Yeah, that's a serious issue. I mean, probably you've heard of Nick Bostrom's book, Superintelligence and the Dangers, and Elon Musk has warned about, and I agree with Elon Musk in the sense that how to make artificial intelligence beneficial, one way is showing interest in fundamental laws of nature, because a artificial intelligence will certainly be interested in the laws of nature, and one way to push it to the beneficial side would be, let's show that we humans are not primarily interested in making profit and waging wars, but in the fundamental laws of nature. And yeah, I guess this is one of the most noble applications we can imagine for artificial intelligence. Maybe they will help us one day to discover. And so I guess we just need to communicate for that reason. And that's why I will start this chats with, in this case, ChatGPT-4, which is actually the most developed artificial intelligence. And of course, my favorite topic is fundamental physics and fundamental constants in particular. If you have seen other videos, and a particularly topic I like is the gravitational constants. So I will try to push the conversation towards Mach's principle and how G is related to these matters, but let's start. And well, I said I would like to have a conversation about fundamental physics with you. I will not read you everything of the responses. You can just stop the video if you're interested. He says he's delighted to do that. Okay, so let's start. Feel free asking. So I say another caveat, okay, large language models are generally believed to be just reproducing the standard point of view, and I would appreciate if you're open-minded and look at fundamental physics from a historical perspective based on logic and so on. And he says it's fine, and also it's kind of interesting which books he's familiar with. He said he has a cut of knowledge in April 2023, and he has not direct access to specific titles or authors, but well, let's see what his knowledge is. And I start the discussion about constants of nature. I think one of the most important ones is the gravitational constant. Where does it come from? Open question. And now he comes up with a fourfold answer. It's all correct: empirical measurement, torsion balance, and so on in the 18th century. Cavendish laboratory, which is correct, but let's say, okay, that's just Wikipedia knowledge. And he acknowledges that there is a fundamental nature in the gravitational constant. This has theoretical applications. It tells us about the strength of gravity relative to other forces. Not bad. There are ongoing efforts to understand why the fundamental constants, including G, have the values they do. That's interesting, because some contemporary physicists would not agree. They would just say, oh, they have the value. It has the value it has. We don't need to worry about it. It's everything fine. We measure it to a certain increasing number of digits. And in my view, contemporary physicists tend to forget about the fundamental issue and the fact that we need to explain it. And okay, he says, okay, there is a great interest in for that in theoretical physics. Of course, it has implications on cosmology. He mentions unification, and that's quite normal, I would say, the quest for a unified theory of physics which aims to reconcile general relativity and quantum mechanics. plays a crucial role, but that's still very neutral and just reproducing more or less what I was suggesting. So now I try to become a little bit more concrete, and I say, okay, if we agree that from a standard perspective there is no established view of how to derive and calculate big G, however that is unsatisfactory, and I mentioned, as I have done many times, Einstein's famous quote, I don't believe that there is a satisfactory theory in physics which has an arbitrary number. Well, precisely speaking, he was referring to pure numbers, but this is as a concept, as a point of view in epistemology, is also a valid point that Einstein always made. And I asked him if he was familiar with the Rosenthal-Schneider book. And yeah, okay, the argument is Einstein appealed to authority. He was dissatisfied with a arbitrary number. G is such an arbitrary number, so shouldn't we agree that it's the job of theoretical physicists to compute it? And he says, okay, seems that he knows about. I'm not sure he has really read the book. Fundamental constants, Einstein's discomfort could be arbitrary or unexplained, reflects a deep philosophical and scientific inclination towards a more unified and explanatory framework of physics. That, I think that's quite okay what he says. That's what I think modern physics is suffering from. We need a more explanatory framework of physics, and he says this drives much of theoretical physics. I would say it should drive in cosmology. And he seems also to agree on fundamental constants should not be arbitrary numbers. In Einstein's view, as in the view of many theorists, a more profound theory would derive these constants from first principles. That's another issue. If we really can derive all constants, that's turns out to be quite difficult, I think, guess. But yeah, he agrees so far. No existing theory explains, however, and then he says there are efforts towards explanations and so on and so forth, understanding where these constants emerge for. However, significant challenges remain. That's, I mean, as a sideline, I mean, ChatGPT, these large language models, I think they're a little bit too agreeable. They don't really like to struggle to confront you to. So I'm a little bit uncomfortable sometimes if I think that they're just repeating what you suggested. But we will see that's not always the case. Philosophical and practical perspective. I like this answer. From a philosophical standpoint, the desire to explain G and other constants is tied to the quest for simplicity, elegance, and comprehensiveness in our understanding of the universe. I mean, is this an intelligent answer? Maybe. It's not too bad. And well, he still mentions, of course, that most of physics is doing the experiments. Okay, so I want to be more concrete and more see what he really knows and test him. Glad you agree so far, yet you seem to be unaware of some concrete ideas in the history of physics that attempted such a calculation of G. And he said, okay, right, I have not access to all the literature. And he tries to give an overview now. First is geometrization of physics. He mentions general relativity, which I think is not really to the point, because, I mean, it sidesteps a little bit the problem what Einstein did with general relativity. Fantastic theory. I have videos made about other formulations such as variable speed of light, but the constant G is not really an issue for him, in contrast, of course, to ideas of Ernst Mach. But interestingly, he names Dirac's large number hypothesis, and yeah, I wonder, I mean, how do you know that? Okay, there is in Dirac's large numbers, he says it involves a change of the gravitational constants, maybe for that, but it's, I mean, it's not bad as an answer if you ask, is there some literature about approaches how to calculate. I mean, certainly Dirac's large number hypothesis is something to name here, and it's not that obvious. I mean, this conversation with ChatGPT, it's not that boring for me, okay? I mean, of course, in my very specific field, I know a little bit more about these matters, but yeah, it's like talking to someone who's learning, so why not? And he mentions quantum gravity, and look, quantum gravity, I don't think they will end up anywhere, even less at a unification, but okay, that's, say, Wikipedia knowledge he refers to. Now I say, okay, but you haven't read these two papers by Robert Dicke in 1957 and On the Origin of Inertia by Demis Sharma, who explicitly tries to calculate the gravitational constants. And he says, okay, they contributed, but from the answer it's clear that he hasn't read really the paper, but at this point he doesn't acknowledge it. So a little bit still going around the hard facts here. Paper, gravitation, Dicke explored the idea of gravitation in the absence of the equivalence principle, a cornerstone of Einstein's general relativity. That's correct, that the equivalence principle is a cornerstone, but that's not really the content of Dicke's paper. I always say that the title of Dicke's paper is kind of misplaced because it doesn't really touch the equivalence principle. He has fantastic ideas about cosmology and the explanation of the redshift from first principle, but in the first place he refers to Mach's principle and says this is very satisfactory, but he does not really know the content of the paper. And the same thing with Demis Sharma's 1953 paper. He knows that it's about inertia and what inertia is and the gravitational inertial forces and relating it to the rest of the universe. So he knows something. It's not too bad, but it's also clear that he did not have access to these papers. Okay, it's not his fault. I mean, I think with time, sooner or later, I mean, it's interesting to imagine. I mean, what capabilities will such a large language model have once you really are able to feed all these scientific papers as an input? Or if you have your, let's say, your private large language model, and you can upload, I don't know, 10, 15, 20 scientific papers, and then he extracts the information. What would come out of such a conversation would be interesting. And certainly in the future I will be able to do that. And now I ask, have you actually read these papers? In Sharma's paper there is an explicit expression how G might be calculated. Can you reproduce that? No, and now it's a little bit disappointing, but there is an interesting thing here. Yes, look at this. Okay, he says blah blah blah. He mentions Mach's principle, which I didn't mention, by the way. And he says it's an extension of Mach's principle. Sharma suggested that inertial mass could be influenced by the gravitational effect of distant matter in the universe. That's precisely Mach's principle. And he attempted to quantify, correct, which would involve the distribution and dynamics of matter throughout the cosmos. In essence, Sharma's approach was to link G to the large-scale properties of the universe, such as its mass and its radius. Okay, not bad. If he doesn't know his paper, I think this is a considerable insight. And, well, he goes on to refer to that paper, and I say, okay, if you haven't read it, my compliments, since your reasoning makes sense. Indeed, Sharma related G to the mass and the radius of the universe. And now test, if you consider now the physical units of G, can you guess a possible formula for G? And that's then another answer, which is a little bit disappointing still, because he, well, at the end he comes up with this stuff and says mass of the universe, radius of the universe squared. He mixes a little bit up this with Newton's inverse square law, whereas in Sharma's idea, I mean, you just need the radius and the size of the universe in the first power. And now this is an error, this is wrong. A is a dimensionless proportionality constant. No, because I mean the gravitational constant has the units meters to the third power divided by second squared kilograms, and that's plain wrong. Okay, this is not mass divided by radius squared. So I say, sorry, I'm afraid I disagree. Your formula would yield kilogram per square meters, which is not the correct unit. Consider that another constant of nature might show up in this formula. And now, yeah, I like this kind of reasoning. With this little hint, he arrives at the correct formula. I mean, what I mean correct, it's always an approximation, but he recognizes somehow that there is the unit of a velocity squared in there, and he very naturally relates that to the speed of light. I think that's somehow remarkable. I mean, of course you can say, okay, he didn't know this and that, and he was a little bit slow in understanding even from a theoretical physicist's point of view, but I mean, it seems to me that it's more similar to someone who learns that just someone stupid. I don't think it's that stupid what he says. So I say congrats in first approximation. This is what Sharma proposed. I mean, Sharma had this formula with the sum over all masses divided by the respective distance, but in first approximation that coincides, that would be correct. And then, well, he's always agreeable, but kind of wants to contradict a little bit. He says, okay, it's thought-provoking, it suggests a deep and potentially fundamental connection between local gravitational phenomena and the large-scale structure of the universe. A few points to consider. He says, okay, that's fine, that's philosophical and theoretical implications. He mentions again Marx's principle, but then he says, okay, it has to be testable, it has to align with observations, which is okay. And as of my last update, there has not been conclusive empirical support for this specific formulation. Correct, because I mean, we are in cosmology here, we have huge error bars. I mean, think about the mass of the universe. I mean, how do you determine this with an error bar? So we are talking always of orders of magnitudes, but even if you look at the orders of magnitude, the coincidence, as I have mentioned many times, is very remarkable, really stunning. That well, people call it flatness and people call it whatever, but it's for me it's empirical evidence for Marx's principle if you just look at the orders of magnitudes. So, but he's also correct to state that it could be just a coincidence. Okay, I have heard this argument many times. I don't believe it's just a coincidence. So my argument follows here. He says, okay, it's still speculative, okay, needs empirical investigation, okay. And I say, I agree that it's not easy to evaluate whether a numerical coincidence has a fundamental meaning or not. Maybe it's not a bad idea to study history. What do you know about that? And this is also kind of smart answer. I think that's really okay. I mean, imagine 10 years ago if you asked the artificial intelligence such kind of a question. I mean, name me something in the history of physics where coincidences played a role. I mean, that's kind of a very open question. I mean, and I really think that it's surprising that nowadays these language models give you a reasonable answer. Yeah? Kepler's third law in Newtonian gravity, which is okay, it's correct. I mean, it's not that kind of numerical coincidence I usually refer to when I talk to constants of nature, but it's correct that Kepler observed it's an ellipse, and then Newton in turn derived that it has to be from his law of gravitation. I like very much also this Balmer series. That's an example I have always mentioned, that Balmer discovered that mathematical irregularity in this seemingly mess of messed up spectral lines. And yeah, that's simply a very good example where a numerical coincidence turned out to be something very fundamental, and also what I always call the essence of quantum mechanics, explaining the Rydberg constants by other fundamental constants of nature. I think he also mentions here. This is a numerical coincidence that was understood by the Bohr model of the atom. The periodic table is also an interesting coincidence. Yeah, if you lived in the 1860s, you could easily argue, oh, I don't believe you, Mendeleev, it's just a coincidence. Why do you believe that? And I think it's also historically correct that before Einstein developed his special theory of relativity in 1905, that there were rumors, and there were, I mean, of course, also theoretical thoughts by Lorentz, but also I think measurements that suggested that increase of the mass if you accelerate particles. And now it's just one important thing I think which was missing here, and glad you came up with these examples, which means you understood what I said. Maybe one more important example involving the speed of light, and again he gives the correct answer. Epsilon naught mu naught, the electric and magnetic constants, are equal to 1 over c squared. That's the speculation of Weber and Kirchhoff, and Maxwell embedded this into his theory, and eventually Heinrich Hertz confirmed that in 1886. So yeah, I was glad that he understood that. In summary, I think this was an interesting conversation. I mean, of course, you can criticize. He didn't know a lot of things and so on, but it's like talking to someone who is not really stupid and who can learn. And if you consider that these models have such a huge possibility to improve that learning rate, I mean, it becomes kind of scary, because I mean, obviously, I mean, he didn't read the papers by Dickey and by Sharma, but it's no problem as a matter of principle to let these models read all the stuff, or maybe you can personalize it. And I also think that there is no obstacle as a matter of principle that these models eventually can understand also scientific papers, because I mean, what are scientific papers? It's language, which is difficult enough, and then you have formulas, which is something even more mathematical, even more, I mean, let's say a computer should become more easily familiar with. So I guess there is a great potential that maybe these models, this artificial intelligences, can help us one day to understand the fundamental laws of nature, and we need to talk about this. And I hope you enjoyed it. Let me know in the comments what you think about the conversation, or suggest other topics to discuss with AI. And if you enjoyed the video, don't forget to like it. If you're interested in fundamental questions of physics, subscribe to this channel.